what we've done in the lectures up until now is covered or introduced data communications and introduced protocols and protocol architectures. And you don't have to draw this, but here's our 5-layer protocol stack that we arrived at, starting from the physical layer, data link layer, up to the application layer. For the remainder of this course, we're going to go through those layers. We're going to start at the bottom and work our way up, starting today at concepts, very basic concepts of data transmission, which is related to the physical layer, and several topics on the physical layer, up until the midterm, where we'll cover the data link layer. And then mainly after the midterm exam, we'll cover the network layer, transport, and finish with 1 or 2 lectures on the application layer. So now we start to go into things in more depth. Up until now, it's been general concepts, principles, protocol architectures. When the midterm exam comes and asks a question, explain the physical layer, what are you going to say? What's your definition or simple explanation of the physical layer? What does it do? Physical layer, remember this is our computing device, our source host. We think if we draw, the link goes into the physical layer. It generates signals to be sent across the link that it's attached to. It takes data from the data link layer coming in. Often we think when we're talking about computers, bits, digital data, zeros and ones coming in, and generates some signal, some physical signal, to be transmitted across our link to the next device. So that's the layer that attaches us to the network, to a link. Data comes in, digital or analog data comes in, signals come out, physical signals, which represent that data. We're going to look at those signals today. We're going to start to introduce the basic mathematics of the signals which are generated by the physical layer. And in the next few topics, we'll look at how do we convert data, bits, into signals. First, we'll go through some very simple terminology. In data transmission, we transmit data from one computer or one device to another via some medium. Those devices are called the transmitter, or in brief, TX, and the receiver, RX. It's just abbreviation for TX, transmitter, RX, receiver. So that's our very basic data communications scenario. Transmit data from one to another via some medium. So the medium is the thing between the transmitter and receiver. It may be a cable, it may not be. In the case of wireless communications, there's no physical cable there, but we still have a medium, which is the air. What goes between this device, the transmitting device, and the receiving device? Some signals. I'll draw a sine wave to represent a signal, but it's more complex than that. The communications is in the form of electromagnetic waves. So we transfer energy from one point to another in the form of electromagnetic waves. The signals, or these waves, may be light signals. If we're using optical fibre, we may transmit light or pulses of light across the cable or across the optical fibre. It may be radio signals. If I'm using wireless, transmit some signal from my antenna and it propagates up to the access point. It may be electricity, some electrical signal. If I'm attached to my LAN cable, which has some copper conducting wires in there. The copper wires conduct electricity. So the electricity is the signal that is passing through our medium. We're going to look at what type of signals and how they are designed today. There are different types of signals, but in general we say that there's some signal sent from transmitter to receiver that represents the data. So we use some physical signal, but the data is carried within that signal. So just some terminology for today, or for now. This medium between transmitter and receiver, we can classify it as either guided or unguided. In simple terms, guided is wired communications, unguided is wireless communications. By guided, we mean that the signal is controlled in where it's sent. The energy is guided or restricted to go in one direction, for example. So when we send electricity through my twisted copper, literally twisted, my electrical wires in here, the electricity flows through the copper conductor. When I hold it and someone's transmitting on here, do I get an electric shock? Do you think? Do you think you'll get an electric shock if I plug this into my computer and to the PC and send data? Will you feel it? No. The electricity does not come out. It's guided inside the copper wire. Okay? There's some insulation there. So this is a guided medium. The signal is guided inside there. Unguided or wireless is when the signal can disperse in multiple directions. There's no strong control on the direction where the signal goes. Me talking, for example, if I turned off the microphone, me talking, we have an unguided medium of the air because the signal, when I talk, basically goes all around me. The audio signal comes out stronger in this direction, but if you stood behind me, you'd still hear me talking. So in that case, the audio signal is across an unguided medium, air, other unguided mediums, water, in theory a vacuum. Guided, wired, unguided mediums, wireless. Another way we can classify communication links is about their configuration, how they are configured. We can say a link or a medium is point-to-point or point-to-multipoint or simply multipoint. Point-to-point is when there's just two devices attached to that medium, two devices sharing that medium. I connect my laptop, if I can get this straight, I connect my laptop to one endpoint of this cable and connect the other endpoint to the PC. With respect to this cable, the medium, there are only two devices attached. When one transmits, it's only one other device is going to receive that signal. That's a point-to-point medium, or a point-to-point link, when just two devices are connected together. The alternative is point-to-multipoint, where, for example, we have one transmitter that transmits a signal and there may be multiple receivers that receive that signal. So one transmission and multiple receivers receive the signal. We have one point to multiple points communication, or simply multi-point medium or a multi-point link. Two or more devices share the medium. Oh, sorry, more than two, not two or more. Two is when we have point-to-point. Two or more than two when we have multi-point communications. When my laptop transmits using Wi-Fi, I say I'm sending some data to the access point. In fact, what happens, it generates some radio signal, and that signal doesn't just go in that direction, it goes all around. So another access point out in the corridor could also receive my signal from the laptop. So in fact, when I transmit a signal from my laptop, it goes in multiple directions. Multiple receivers may receive it. So Wi-Fi is generally considered a multi-point medium, and many wireless communications are multi-point. Depending upon the configuration, we may need different protocols to make them work well, especially when we come to the data link layer. There are different data link layer protocols which are designed specifically for point-to-point and others for point-to-multipoint. We'll come to that later. The other way we can classify links and mediums is the direction that which we send our signal, in which we communicate between the transmitter or between two devices. We have simplex communication, which is one way only. Television is the example. With TV, there's a TV tower. Let's say the TV station has a transmitting tower. They transmit some television signal. Everyone who has an antenna on their television will receive that same signal. So it's multi-point, and the TVs do not send back to the TV station. Okay? Your TV just receives, it doesn't transmit. So television is an example of simplex communications, one direction only. For example, from A to B. If we have a link where we can only transmit from A to B, we cannot send from B back to A, then we call that a simplex link or a simplex medium. Half duplex is where we can send in both directions but not at the same time. A can transmit to B across our link, or B can transmit to A, but they cannot do it at the same time. Then we would call that link a half duplex link or a half duplex medium. Examples that you may know about is the police radio or the CB radios, where you press a button and talk, the other person hears you, then you release the button, and then the other person presses the button and talks, and then you hear them. That's that's half duplex communications, in that only one is communicating at a time, but it can go in opposite directions. And then full duplex. If we can use the medium to transmit in both directions at the same time, then that's considered full duplex. A is transmitting to B, and at the same time B can be transmitting separate data back to A. If that's possible, it's a full duplex medium. So this is ways to classify transmission mediums. It's either guided or unguided. The link can be configured to be point-to-point or multi-point, and the direction of communications can be simplex, half duplex, or full duplex. And the example I always use for the last few years is, what about this lecture? When we're in this lecture, we're communicating. Hopefully some information is getting to you. Are we using a guided or an unguided medium in this lecture? You've got two choices, guided or unguided. Hands up for guided. I want to see everyone's hands either for one of the two. Is this medium using a guided? Is this lecture using a guided medium? Hands up. No one. Unguided? Hands up if you don't know. Unguided. Why is it unguided?
Because your voice passes through air.
Because my voice is passing through air. Yeah, I would say in the majority of this communications it's unguided. It's a little bit more complex because I have the microphone. My voice, the audio signal coming out of my mouth, goes to the microphone. That's an unguided medium. It's going through air. In fact, when I talk without the microphone, you'll also hear me around here. From the microphone to the wireless transmitter, it's in fact a guided medium. Then to the wireless transmitter to the receiver, it's again unguided. Guided through the cabling up to the speakers, and the largest distance probably is from the speakers to your ears. That component is unguided. Again, transmitting audio signals through the air. Is this lecture point-to-point or multi-point configuration? Point-to-point or multi-point? Hands up for point-to-point. Let's see some hands. Hands up for multi-point. See some more hands. Why is it multi-point? I saw your hand then.
I don't know. Yeah.
Again? More than two devices sharing medium. What are those devices? What are the devices sharing the medium in this lecture? What are the devices? Yes, it's written on the screen. Multi-point, more than two devices share the medium, but in this scenario of the lecture, why is it multi-point? Anyone can help him? Why is this lecture multi-point? Because
you're the one who's the lecturer, and all students, it's like as devices, and you transmit your voice in the air.
I transmit my voice in the air and everyone receives it. Okay? For example, when I talk, I'm transmitting information as some audio signal. And that one transmission, everyone receives that one transmission. You all hear it. So in fact, we have communicating not just from one person to another, we're communicating from one to many. It's point to multi-point communications. What about this lecture? Simplex, half duplex or full duplex? 3 options. Hands up for simplex. Okay, anyone else? Simplex. Is this lecture simplex, using simplex communications, half duplex or full duplex? We'll try again. Hands up for simplex. Okay. Half duplex. Come on. Full duplex.
Yeah.
Those who choose full duplex are going to fail. Those who choose simplex may be true, but it shouldn't be. Half duplex, it should be. Simplex means that one person talks, no one responds. Of course, in this lecture, you're supposed to ask questions.
No, I'm suggesting like simplex is like we're looking at the monitor right now.
When I mean this lecture, I mean the audio communications. All right, let's ignore the video, the image. Let's think about audio. A lecture, okay, I talk, that's one way of communications from me to you. If it was only that, it would be simplex. If you also talked, then it's not simplex, because it's also communications back. If you are talking when I'm talking, we have full duplex, and I don't want that, okay? I want half duplex. That is, either I'm talking or you're asking questions, okay? That's what we should have in terms of our lecture communications. What about when I connect my LAN between laptop and PC? Guided or unguided? Using this cable. Guided. Point to point, multi-point. Point to point. There's just 2 devices connected that medium. Simplex, half duplex or full duplex? Some say half, some say full. It's definitely not simplex because I can send to the computer and the computer can send back. It depends. In the old technologies, in the old LAN cards, it was half duplex, but now it's full duplex. And the way that they achieve that, in fact, is use 2 sets of wires. You remember there's 8 different wires in here. We use some to transmit in one direction and some to transmit back. From the perspective of the computers, they can transmit and receive at the same time. It can be full duplex communications. We'll see other examples of them as we go through the course. Just some terminology and classification of links and mediums. So we send a signal from transmitter to receiver. we want to understand what that signal looks like or what it is made of. It's an electromagnetic signal. It's the transfer of some energy from one point to another. The examples we commonly use are electricity, light, some radio signal if using wireless communications, and so on. We actually want to send data from transmitter to receiver. We send that data as some signal, where we somehow map the data, whether it's bits or some analog data, into some physical signal that we can transmit. What we want to cover today is the very basics of what those signals look like from the perspective of the people who create or design the signals. Here's a LAN card, an old LAN card. Someone had to design this, okay? Someone had to build it. And so that when I plug a cable into this LAN card and plug it into this other one, which is made, assume it's made by two different companies, okay, two different LAN cards, so that they can communicate with each other, they need to follow the same protocols. So in fact, there will be a standard that says, for LAN communications, use these protocols. So if both companies follow the same standard, they should be able to talk to each other if we plug cables in. The people who create the standards and the people who design and build the transmitting and receiving devices have to select the signals to transmit between them. The way that they design the signals is, or the very basics at which they design signals, is they look at the signals from the perspective as sine waves, sinusoids. Because we can analyse sinusoids relatively easy using mathematics, the communication signals, however complex they may be, are eventually broken down in theory to being a set of sinusoids. We're going to look at the very basic structure of a sinusoid signal and then see how we can take a sine wave, in fact multiple sine waves, and combine them together to get a different communication signal. Today we'll just look about the time domain. Later, maybe tomorrow, well, tomorrow we'll look at the frequency domain. We'll come back to that. That is, we have some signal and it changes its amplitude, its magnitude over time. For example, electricity, we have the voltage changing as a function of time. Some terminology still. The signals that we can transmit from A to B, we could classify as either analog or digital. Analog is a signal that varies continuously over time, like the top diagram. Digital, we maintain some level for some period of time and then instantly change to another level, and so on. In practice, we cannot do something instantaneously. It takes some time to change, but we think of it as a digital signal because it's at one level, let's say 0 volts, and then at some point in time it instantly changes to +1 volts, a different level, and changes. And we use analog and digital signals to represent the data that we want to get from A to B. Any signal can be considered periodic or aperiodic. Periodic, it repeats, some part of it repeats over time and continuously repeats. These two examples are periodic. Both are periodic signals. We see the sine wave, it starts at time 0 and gets to some point back to a magnitude of 0, and then the same signal is repeated, and again and again and again. Okay, simple. And it has some period, the duration in time of one repetition, one cycle. So the period of this signal. And this square wave signal, digital signal, is also periodic if we continue in time. It's just this component repeated and so on. It also has some period. This signal at the top is aperiodic. There's no part of it that's repeating over time, at least in the time frame we look at. These are things you know, very basic. So when we want to send a signal from A to B, we need to construct a signal that meets certain requirements. We'll see the requirements later, but the people who design the signals to be transmitted design them and analyse them from the perspective of looking at them as sinusoids, as sine waves. So what we'll see is we can treat any signal that we want to send as a combination of different sinusoids. So the main or the fundamental thing that we need to cover is, well, what is a sinusoid? What can we vary in a sine wave? And how can we combine them together to get different signals? So for now, we're going to look at, this is high school mathematics, the sine function. And look at some characteristics of it so that we can set up the real communication signals later. A sine wave or a sinusoid can be expressed as this equation mathematically. The signal amplitude or the signal strength, S, as a function of time t equals the peak amplitude, A, multiplied by sine, the sine function, 2 pi ft, 2 and pi are constants, f is the frequency of the signal, t is the time, plus the phase, phi here. That's the general form of our sinusoid. The three things that we can vary are the peak amplitude, A, the frequency, F, and the phase, phi. By changing those three values, or any of those three values, we'll get a different shape sine wave. If we have some signal as a function of time, the signal strength as a function of time, so let's say measured in volts, then at some point in time, t equal 1 second, we can find out the current voltage by plugging in t equal to 1, it's in 1 second. If we know the peak amplitude of that signal, which is also measured in volts normally, the frequency of the signal measured in hertz, and the phase of the signal usually measured in radians. We'll use these 4 examples to just show those concepts from the mathematical point of view. Focus first on the top left plot, ignore the others. I'll write the general form of the equation from the previous slide. Now let's, in the top plot, you see in the caption there are some specific values which are used to generate this plot. It's uppercase A equals 1, F equals 1, and the phase equals 0. Let's write the equation, maybe over here. I'll call the top one because it's figure A. Let's call the signal SA of t. That is, the signal strength as a function of time can be expressed by the following equation, or following by this equation. It has a peak amplitude of, by looking at the graph, what's the peak amplitude of this signal? Looking at this one, what's the highest point? 1. It has a peak amplitude of 1. That is, uppercase A is 1. Then the general form is sine 2 times pi times f times t. What's f? What's the frequency of this signal?
1.
The answer is here. It's easy. Why is it 1? Well, graphically looking at it, how many times does the sine wave repeat every 1 second? 1. Because here's 0, time 0, here's time 1. We see it repeats exactly once in that 1 second. So it has a frequency of 1. F is 1. Yeah. 2 times pi times f. In this specific instance, f is 1 times t. And the phase? It's given here, and the phase, we'll explain that when we cover a signal with a different phase. There is zero, the phase is zero in this case. The phase is the shift of the signal relative to some origin point. Think of a sine wave. When time is zero, the signal amplitude should be zero, with zero phase. If we shift that some way, then it means when time is zero, the signal amplitude will be some other value. We'll see later, here's an example of a different phase signal. Time is zero, the signal amplitude is different from the previous one. Simplify this, it's simply sine 2 pi t. If I give you this equation, Sa of t equals sine 2 pi t, you could plot this. Okay? You just use your calculator and you could calculate, okay, if t equals 0, the answer, well, the value of Sa will be 0. If t equals 0.1, then the value will be somewhere here, 0.4. If t equals 0.5, then sine of pi t of pi is 0, and you could plot that if you had a calculator and a graphing paper or a computer. That's our basic sine signal, sinusoid. The three values that we can change are the peak amplitude, frequency and phase. Here we have a peak amplitude of 1, frequency of 1, phase of 0. In the general equation, A, F and phi. Let's look at a different signal, the one on the top right. Let's call it SB. What's the equation? SB of t equals the top right.
0.5
Okay. Peak amplitude is now 0.5. We see comparing A versus B, everything looks the same except it's squished from the amplitude perspective. That is, the peak amplitude is half of B, so that we have 0.5 sine. What's the frequency?
1.
Again, within 1 second, there's just one cycle. The frequency is 1 hertz. So we still get 2 pi t, 2 pi times 1 times t, which is 2 pi t. And the phase is still 0. There's no offset or no shifting of that graph, that plotted signal in any direction. 0.5 sine 2 pi t, half sine 2 pi t. SA is sine 2 pi t, SB is 0.5 sine 2 pi t. On the board, I will often use the decimal point in the middle, not down here. Don't get confused, because sometimes I use a dot to represent multiplication. Signal C. Peak amplitude of the bottom left signal. Peak amplitude goes up to 1. 1 sine frequency. We see now that between time 0 and time 1, there are 2 repetitions. That is, we have a frequency of 2. 2 repetitions per second means 2 hertz. So it's 2 pi times the frequency times t, which will be 4 pi t. 2 times pi times 2 times t. The phase is still 0 in this case. Simply sine, I'll remove the 1, sine 4 pi t, half sine 2 pi t, sine 2 pi t, and the last one, SD of t. Peak amplitude is 1. Frequency is 1. The phase is not 0 in this case. From looking just at the plot, I wouldn't expect you to tell me what the phase is. Maybe with a calculator or a computer you could determine the phase, but by just looking at that plot, it's hard to know what the exact phase is. The caption gives it to us. It's pi over 4 radians. Visually, the phase shifts the signal along. Take the original signal with a phase of pi over 4, you can imagine that it's been shifted back. So now at time 0 it starts here. It doesn't start here at 0 magnitude, it starts at this point, which is 0.7 something. I don't know the value. It's been shifted because of the different phase, or the non-zero phase here. Other than that, the frequency is the same as A. The peak amplitude is the same as A. It's just it's been shifted along in time. So, again, from basic high school mathematics for a sinusoid, a sine wave, there are 3 things we can vary to change its shape: the peak amplitude, the frequency, and the phase. Peak amplitude changes its height, if we look at the plot. Frequency changes how often it repeats in 1 second, squishes it that way, and the phase shifts it if we look at it visually. So we have 4 different signals in this case, all sinusoids with just different values of amplitude, frequency, and phase. Yep. How do we know the value of the phase? You do not just by looking at it. That is, just by, if I just give you this plot, I cannot expect you to find out, well, what is the exact value? Unless maybe if you have a computer, if it's on a computer, you could find out the value. But going the other way, if I give you this equation, what would you do to plot this? Well, you just plug in values of t. If t equals 0, then we get sine 2 pi 0 plus pi over 4, which is sine of pi over 4 in radians. And you'll plug that into your calculator and you'll get this value, which is 0.7. And then you'll try t equal to 0.0001, and you'll get the next value. And you'll keep plotting it, and you'll get these values. So visually, it's not easy to determine the phase. You need a computer or so on to generate that. But understand what it does to the signal. It shifts it along. Why do we cover this? This is simple. We cover this because the signals which are generated by real devices, when someone designs those signals, they look at them from the perspective of sinusoids. That is, the real signals can be seen as a combination of many different sinusoids. If you add 2 different sinusoids together, you'll get a different shape signal. If you add many together, you can design the signal that you want to achieve. So people who design the signals to be transmitted design and analyse them from the perspective of sine waves or sinusoids. That's why we would just want to introduce that concept. We'll come back to that in a moment. This is a signal in the time domain, the signal amplitude versus time. We'll see that we can also look at the signal from the perspective of the frequency domain. But before we do that, your quiz was finished this morning, I want to have a look at one concept that was tested in the quiz, which was unsuccessful, and that you didn't get good grades. So let's have a look at the quiz to change the topic for a bit. And this is the histogram of the results for the first 4 quizzes. You can't see the values, but on the left of the plot is the 0 marks. On the right is the full marks. So in quiz 1, most people got high marks. The average was 66%. Quiz 2, still people were getting high marks, 70% average. Quiz 3, still not bad, 57%. People are around here. Quiz 4, average 22%. Most people got 0. Some got 1 out of 4. Not many people got full marks. Why is that? Why? Because you do not understand some of the performance aspects. So let's look at just one of those performance aspects, which is delay now. Maybe we'll look at throughput in another example in another lecture. From memory, there are 4 questions in the quiz. One was about, I think, transmission delay. One was about propagation delay. One was, I think, about total delay, a longer calculation. And the last one was about throughput. That is, there's many overheads from the protocol stack. Calculate the throughput. Today we'll just look at delay. And what I'll do is go through an example to try and explain again the concepts, or the components of delay. You don't have this. I only created it yesterday. It's on the website now. You can have a look. I don't think there's any need to write it down. You can download and print it later if you want. Try and follow the example. It's not in your handouts. We have a simple question. There's a link from computer A to computer B. Computer A wants to transfer 5 bits of data, and the link is 4.5 kilometres long, and the data rate of the transmitting device, so the thing that transmits the data, can send at a rate of 500 kilobits per second. Question is, how long does it take to get that data, all 5 bits, from A to B? I'll just draw that. A link from A to B, 4.5 kilometres, data rate of 500 kilobits per second, and 5 bits of data. That's what you have. So we'll go through this. It will demonstrate the concepts again of the components of delay, and especially propagation and transmission delay. This question we're focusing on just 2 of the 4 components of delay. There are 4, which are transmission, propagation, processing and queuing. In this case, because there's nothing given in the question about the processing and queuing, and in this course we don't know how to calculate them. So I either give you the values of processing and queuing, or you assume they're 0. So in this question, assume processing and queuing delays are 0. We only need to calculate transmission delay and propagation delay. And we'll do them separately. First, transmission delay. Again, don't worry about copying down everything I show here. You can maybe easier to look at it in the slides later. So the question now is, what is the transmission delay? Well, I'll use this diagram to illustrate how we view or calculate the transmission delay. What this diagram shows is our 2 computers, A and B. And it shows, or we're going to use it to draw what happens over time. Starting at time 0, when we first have the data to send, And time increases as we go down, and we're going to show, okay, eventually the data is going to arrive at B. How long does it take from time 0 until all the 5 bits are at B? That's what we want to calculate, and we'll try and draw it here to help our calculation. The units of these numbers will be microseconds. So the first thing that happens, computer A has a transmitting device. It has 5 bits of data in memory, and it starts transmitting those bits. Okay? A bit is not transmitted instantly. We know that we don't send a bit, in fact we send a signal, some electrical signal, for example, if we're using this LAN card. This generates some electrical signal which is transmitted out of the socket onto the cable, onto the copper conductor. And it takes time to transmit the signal which represents a bit. Okay, so it's transmitting the signal representing 1 bit for some period of time. And it transmits 1 bit at a time. It transmits the first bit, and then the second bit, the third bit, and so on. So if we start transmitting the first bit at time 0, the question is, when do we finish transmitting that first bit? Or how long to transmit that first bit? What's the answer? Calculate it. How long to transmit just 1 bit from my computer out onto the link? Not 5 bits, just 1 bit. Data size, someone's mentioned data size. What are you going to do with it? Data size divided by data rate. And the value is, or the answer is? So we're looking just at transmission delay. Transmission delay, I'm focusing on first. 1 bit to transmit. 1 over 1. We have a data rate of 500,000 bits per second, 500 kilobits per second. So in 1 second we can send 500,000 bits. Therefore 1 bit will take 1 divided by 500,000 seconds. 1 bit takes in one bit, and the rate is 500 kilobits per second, 500,000 bits per second. Bits divided by bits per second. And you can use your calculator to do that, and it's 2 by 10 to the minus 6 seconds, or 2 microseconds. If it takes 2 microseconds to send 1 bit, it would take 1 second to send 500,000 bits. That is 2 times 500,000 equals 2 microseconds times 500,000 is 1 second. So we can say when this device is generating a signal to represent that first bit, it takes 2 microseconds to transmit that signal. It generates the signal for 2 microseconds. It's transmitting for 2 microseconds, which is really just data size divided by data rate. Data size 1 bit, data rate 500,000 bits per second. 2 microseconds. We can draw that we start transmitting the first bit at time 0. It takes 2 microseconds to transmit that first bit. Therefore, we would finish transmitting at time 2, if the units here are microseconds. So I've drawn the time spent transmitting the bit as this grey rectangle. The grey rectangle starts at 0, finishes at 2. And I'm going to draw the subsequent bits shortly, just so we can work out the total time to transmit those bits. What happens is I have 5 bits to send. I transmit the signal representing the first bit. Immediately after that, I start transmitting the signal representing the second bit. And the second bit takes how long? The second bit will take 2 microseconds, the same time. Every bit will take the same time. We're sending at the same rate or speed. So the second bit will be finished transmitting at time, what time? 4. The third bit times 6, 8, and the 5th bit, finished transmitting at time 10. That is, the job of the transmitter is finished now for this data. It had 5 bits to send. Every bit took 2 microseconds. Therefore, it will take 10 microseconds to transmit all 5 bits. That's our transmission delay. We're finished in the first part of the question. Transmission delay for our 5 bits is 10 microseconds. Of course, you don't have to go through these steps. You can simply say, okay, 5 bits divided by 500,000 bits per second equals 10 microseconds, if you do the calculation. So we have our transmission delay. The time it takes our transmitter to send those bits out. When my transmitter sends those bits out, in fact, they go onto the cable, onto the link. Okay? The electrical signal goes onto the copper wire, and that electrical signal propagates along the copper wire. It travels along the copper wire. And the time it takes to travel from one endpoint to the other endpoint of that copper wire is the propagation delay. That's the next component we want to calculate. Transmission delay is 10 microseconds. Therefore, the next part, what is the propagation delay? Is distance over speed. We'll try and draw the propagation delay as well. I'll go back to the start. I'll remove the transmission time, come back to our first bit again. I start transmitting the first bit at time 0. And then the signal representing the start of that transmission comes out onto the cable and flows through the cable the 4.5 kilometres until that signal reaches B. The question now is, how long does it take that signal to get from A to B? How long for the signal to propagate from A to B? Calculate it. And someone gave you a hint, it's the distance that the signal needs to travel divided by the speed at which that signal travels. Calculate the propagation delay for a signal coming from A to B. Anyone have an answer? What's the distance? What's the distance? What is the distance? 4.5 kilometres. What's the speed? You give me the number, what do you call that? Speed of light. let's write the values. It needs to travel 4.5 kilometres and it goes at 3 by 10 to the 8 metres per second. Why do we use this value? Well, that's the upper limit at which any signal can travel. Okay, the speed of light. We cannot go faster. In reality, the different media lead to different speeds. The copper wire, the speed of electricity varies upon the wire and the insulation. Okay? It will be less than this. Maybe the speed, and it depends upon the actual wire or the cabling, maybe it's usually between 60 and 80% of the speed of light. Maybe 2 by 10 to the power of 8 metres per second in real life. But in this question and in most questions, unless I tell you the speed of transmission in that medium, you can assume the speed of light. It just makes our life a little bit easier. What's the answer? We need to 4,500 metres, 300 million metres per second. $45 divided by 30 is 1.5. 1, 2, 3, 4, 5 by 10 to the power of minus 5 seconds. You can use your calculator, don't worry. 1.5 by 10 to the minus 5 seconds, or 15 microseconds in this case. So you need to know that the propagation delay depends upon the distance and the speed at which the signal, not the data rate, but the speed at which the signal travels, the speed of light, for example. Transmission delay depends upon the data size and the data rate, the speed at which the computer transmits data, bits per second. 15 microseconds from when we start transmitting the first bit until when that signal is received by the computer B. And I draw it like this. At time 0, computer A starts transmitting. It produces an electrical signal. That signal needs to travel 4.5 kilometres. It travels 4.5 kilometres, it taking 15 microseconds, therefore that signal is received at computer B at time 15. The signal representing the start of the first bit. But computer A is transmitting the first bit for 2 microseconds, so it's generating an electrical signal for 2 microseconds. So when computer A is finished transmitting the first bit at time 2, that last part, or that last signal of that first bit, takes also 15 microseconds to propagate. So computer B receives the signal representing the end of the first bit at time, what time? End of signal representing first bit is received at time, what time? We start transmitting at the first bit at time 0. B receives that at time 15, 15 microseconds later, propagation delay. The last part of bit 1 was transmitted at time 2. It also takes 15 microseconds to propagate. B receives that last portion of the bit at time 17. That's just bit 1. So from B's perspective, bit 1 is started to be received at time 15 and finished at time 17. And then it has bit 1. It's in the memory. The same happens for the remaining 4 bits. Transmit bit 2, bit 3, bit 4, they all take time for the signal representing those bits to propagate. If we look at the 5th bit, computer A transmitted the last signal representing the 5th bit at time 10. It takes 15 microseconds to propagate, therefore received by B at time 25. 10 plus 15. At time 25, computer B has received all 5 bits. And that's our total delay in this case. So we have our answer. If A starts transmitting at time 0, B will have received all the data 25 microseconds later. So we say the total delay is 25 microseconds, which is simply transmission delay plus propagation delay. Any questions on this diagram, the concepts we've covered? It's a recap of what we tried to explain but maybe didn't get through clearly last week's lectures. So we have our answer, total delay of 25 microseconds. 10 plus 25. Now you don't have to draw that diagram to find the answer. You just need to recognise, okay, processing is 0, queuing is 0, total delay is the sum of the 4 components. Transmission, data size divided by rate, 10. Propagation, distance divided by speed, 15. Total, 10 plus 15, 25. So, if you have quiz 4 again, or I give you quiz 4 in the exam, the midterm exam, same questions. There were 3 questions about delay. Will you get all of them correct? Any questions about how or the concepts of delay? I think from memory, one of the questions in the quiz was calculate transmission delay. Another question was calculate propagation delay, so they were the simple ones. And then there was a harder question, also about delay, but had multiple components. It was something like, where's all my pens gone? I don't remember the exact question, but it was similar to this. We have one computer, I think it was similar. We have 3 computers, 2 links. And well, there's either 3 or just 1, but the concept was that, well, the question was, A sends a message to C of some size, C sends back a reply. What is the total time? What is the response time? Let's say I send a request from my web browser to the server, the web server sends back a reply. How long between when I send the request to when I receive the reply? It just involves calculating the delay, but now across multiple links and computers. Remember that delay is additive. The delay in each component, to get the total delay, you just add them all together. What we went through is a calculation for propagation and transmission for one link. When A sends to B, you can think the time, there's a transmission delay. It depends upon the link speed and the amount of data. And there's a propagation delay. The data arrives at B. B may process that data. There may be some processing delay in B. Maybe also some queuing delay in B. Depends on what the question says. Then B sends the data onto C. So we calculate the transmission delay again and the propagation delay for this link. We transmit from A to B, it propagates, then it's all received. B transmits from B to C and it propagates. So in such a question you need to calculate the transmission delay and propagation delay for each link. Twice in this case. Let's say, I can't remember the question, but if C processes and then sends back a response, again, the time to transmit and propagate in this direction must be calculated. We transmit and we have propagation. Maybe there's some processing and queuing at B again. And then B back to A. And possibly there's processing in A. Depends on the setup of the question. The total delay now is the sum of all those components. Transmission plus propagation plus processing plus queue plus transmission, propagation, processing and back. So delay is additive in this case. You need to calculate the values or find the values for each of those components. The questions varied among students. The way to remember this, 4 components. Think of transmission and propagation components for a specific link. You see how I draw it? The link from A to B, there's some propagation delay, there's some data rate and therefore some transmission delay. The link from B to C, there's a different transmission and propagation delay. And from C to B, going back, different again, and from B to A. The other 2 components, processing and queuing delay, think of them happening inside computers. A may have a processing delay, B may have a processing and queuing delay, C processing. Of course, in a question, they would be given to you, the values. You just need to sum them all up. The mathematics is simple. You just need to know the concepts of the 4 components of delay and how to calculate transmission and propagation delay. Then you can add them all up to get your final answer, the total delay. Any questions on think of processing delay as the time it takes your computer to, the CPU to process the data. It looks at it, does some operations, usually quite small. Queuing delay is normally, and it doesn't always occur, occurs when multiple people are sending via a device. And the data, or the packets, cannot be sent immediately. Many packets are at B to send to C. You can only transmit one packet at a time. Therefore, other packets will have to wait in a queue before they're sent, incurring some queuing delay. When we look at networks, because really this is a network, not just a single link, there's 2 links. When we look at networks, we'll see at these intermediate devices like B, some more detail of how queuing delay arises. And it can be significant in some cases. In the internet, it can be quite large compared to the other components. Over a single link, just A to B, usually queuing delay is very small or 0. Usually there's no queuing delay. It's the transmission and propagation that are significant. 5 minutes remaining, recap on what we know about signals so that tomorrow we can cover frequency domain concepts. Communication signals which are generated by our transmitters have different characteristics, but when we design them from the perspective of taking simple sinusoid signals and combining them together. Here's an example, and this is the last thing we'll cover today, this example equation here. S of t is the sum of two components. I'm going to separate the two components for S of t. We see it's this 4 divided by pi times by sine 200 pi t plus a third sine 600 pi t. Let's say S1 of t is 4 divided by pi sine 200 pi t. S2 of t is 4 divided by 3 pi. Where did that come from? 4 divided by pi times by 1/3 sine 600 pi t. Then we can say the equation on the screen, S of t, is simply S1 of t plus S2 of t. That is, the signal we have here is a combination of two simple sinusoids. S1 of t, amplitude, S2 of t, some peak amplitude. They're easy. What's the phase of S1 of t? Remember our general equation, A sine 2 pi ft plus phase. The phase is 0. There's no phase component here. Same with S2 of t. Phase. What's the frequency of signal 1? What's the frequency of S1? I almost heard it. No? 100. Go back to our general equation. Where is it? A sine 2 pi ft. 2 pi ft, we have 200 pi t, therefore f must be 100. And of signal 2, the frequency is 300 hertz. 2 pi ft. 2 times pi times 300 gives us 600 pi t. Separately, if we have two signals, S1, S2, they have some peak amplitude, they have 0 phase, they have different frequencies. Note, F2 equals 3 times F1. When we want to design a signal, we can break any communication signal into their component sinusoids. S of t on the screen has two components, S1 and S2. Here's a plot. The top one is a plot of S1, just one sinusoid. This middle plot is the plot of S2. Again, a simple, we expect that shape. And the bottom signal is a plot of the one equation on the screen, S of t, the sum of the two. See, we get a different shaped signal here. And we can combine sinusoids in some way to produce the signal that we'd like to transmit. And we can analyse signals which are transmitted and by breaking them into their component sinusoids. So everything is based upon a simple sinusoid, sine wave. I do not expect you to draw this given the equation. You need a computer to draw this. This is a simple case. You can add many component sine waves together to get a much more complex signal that you'd want to transmit. And that's what communication designers do. The people who design the signals that these are going to send, design them as a combination of different sinusoids and analyse them from the perspective of one signal is broken into component sinusoids. Tomorrow we'll show you how we can represent this signal, in fact each of these three signals, in the frequency domain. But we'll do that tomorrow. Finish for today, out of time.